Hey, welcome everybody. Welcome to my bright room right here. All of a sudden it's super bright. I know usually I look dark and mysterious in most videos, but I'm very bright and visible this time. It's kind of awkward. Anyways, we're on day 2 of section 4.2, my friends. That's right. The name of this section is, again, proving a quadrilateral is a parallelogram. If you watched last lecture, if you did the last lesson, you know that there are 5 ways to determine that a quadrilateral has got to be a parallelogram. So, hey, we're good to go. So you might be wondering, why are we doing a second day? Well, are there more? Are there going to be more than 5 ways? Well, if you did the reading last time, no, there's just 5 ways, okay? 5 ways to prove that a quadrilateral is a parallelogram. You have the definition of a parallelogram, and then you have those 4 theorems we did last time. Okay, so you may be wondering why we're spending the second day on this if there's not another way to prove a quadrilateral is a parallelogram. Well, my friends, we have some theorems today where the proofs of those theorems are, they're just mentioning one right now, right? One is basically where we left off yesterday. This is the next thing they write in the book. They say the proof of the following theorem is based on what you have learned about parallelograms. Okay, so what that kind of suggests is that there is kind of like a corollary, right? A theorem that is related to what you know about things you can say that in order to establish that something must be a parallelogram, there might be a theorem that follows directly from it. So it's kind of a stretch what they do in this section, but hey, they're just like, let's just tack on 2 more random theorems that have to do with parallelograms, and we'll call it a day, right? You get six total theorems in this section. You got 4 last class, you're getting 2 today, but the ones you're getting today, okay, the reason why this whole build-up was the way it was is because the ones that you're getting today feel kind of different, right? They're different than those other 4, which had to do with getting a quadrilateral being a parallelogram. So without further ado, let's jump into it today and figure out what else it is we can say using parallelograms that will follow from what we've learned about parallelograms. And let's conclude section 4.2, shall we? Go well, but then man, I just knocked that one out of the park. That was so good. Okay, anyways, if you weren't looking close attention, so remember what I told you in that last slide, right? You're going to get a following theorem that has to do with parallelograms, right? That's what the last slide said. And as I just fade in this diagram, okay, this is also on page 164 as well, but as I just fade in this diagram, let's take a look at this. What does this diagram have to do with parallelograms? Because it said, mind you, we all read it together, the following theorem has to do with what you know about parallelograms. Look. Let's look at this. Wait a second. Okay, that's the last time I've done that fade in right here. Let's just pause for a second, look at it. What the heck does this have to do with parallelograms? Do you guys see parallelograms here? Yes, well, it's a little bit tricky here, but notice this here. We actually do have parallel lines. We have a pair of parallel lines here. We have a pair of parallel lines here. And if 2 lines are both parallel to the same line, then they're parallel to each other. So we actually have a set of 3 parallel lines, right, that are all parallel to one another right here. Okay, so we do have parallel lines, but does this here ABYX and ACZX or BCZX or any of those parallelograms? No, those look like trapezoids, which we've yet to define, but we'll define in the next section, I believe. So we actually don't see parallelograms, but this problem is going to have to do with parallelograms. So maybe look at it. Maybe look a little closer. What might a parallelogram help us prove in this situation? Well, I have something interesting marked up other than the fact that we just have both, all 3 of these lines are parallel to one another. This conjecture is basically, remember, a conjecture is an unproven scientific theorem. So I'm going to make a conjecture here, given what's given over here. Because notice here, we're given 3 parallel lines. And with those 3 parallel lines, what do we notice that's going on with line AC? This line AC right here. Well, these 3 parallel lines, what are they doing to line AC? Line AC. It's creating what? Okay, and then why is this line drawn in? So again, this diagram here has to do with this theorem we're going to prove. So what we're playing right now is predict, right? Predict what this theorem is based on what's drawn, based on what's given to us, and what is it that you think that we can prove here, right? Prove in the situation, okay? So conjecture, right? What was our conjecture here? So if I have everything marked up, what's our if statement? Our if is, if we have what? Okay, if we have three parallel lines, okay, so that's how our theorem's going to start today, the one we're going to go into. Oh, and then look at that. It just kind of blended in there on the left. Draw your attention to it. So if we have three parallel lines and they cut two congruent segments on one transversal, we got to think, we got to finish our conjecture here. So hold on a second. Let's just read it closely, make sure to understand what it's saying so far in our given premises. So if we have three parallel lines and they happen to cut, right? Because of three parallel lines, when we run a transversal through it, there'll be two kind of segments within the interior of the lowest line between the middle line and then the highest line between the middle line. It'll create two different segments. If those three parallel lines happen to cut two congruent segments on this one transversal right here, what is it do you think we're going to prove here about this transversal? Well, it's also going to cut, or will it, right? We got to prove it as a matter of fact here. Will it prove that on this transversal, for instance, it will cut two congruent segments as well? So here's how it's written out. And there we have it. Let's read it in here. Okay. Then those two parallel lines cut off two congruent segments on any transversal. Those three parallel lines, right? Cut off two congruent segments on any transversal. All right. So that was a big windup. You might be kind of overwhelmed by this. You're like, Mr. Ford, you've been saying a lot and making it so complicated. So let's just take a breath and let's just reread this conjecture here. And then we'll see if we can prove this theorem. So if three parallel lines cut two congruent segments on one transversal, I pause here because look, it's hard to, I miss the fact that these are three parallel lines. They cut off, right? Because we have a transversal running here. They cut off two congruent segments. Then we can make the conclusion that on any other transversal, so here, transversal XZ, we can call it XY if we want to, that the two segments that got cut off here, that they would have to be congruent to each other. Not to this, right? Not to these segments over here, but just to each other, okay? So you might be thinking, Mr. Fortin, again, what the heck is this diagram? What is this? Well, this diagram is going to get us to prove other things in the future. So that's why they're laying it out here for you. This is just kind of an in-between type proof. But it's important because, if it kind of tells us something about if we have three parallel lines, how it preserves distance, that basically distance between these two lines and these two lines will be the same, regardless of how you're measuring distance. Normally, you measure distance through the perpendicular segments, right? Perpendicular transversals. But even if you're just measuring with lines like this, transversals like this, it's going to cut off two congruent segments in any of those instances. So this will be something that will be coming up in proofs in the future, and it's an application involving parallelograms. Okay, so without further ado, right, do you think you could reason through this / prove this? And again, I keep going back to the parallelogram idea because what the heck does this have to do with parallelograms? That's my little hint to you. I'm going to see if you can maybe figure this out on your own. I'm going to give you about 2 minutes to think about it, okay? Maybe slice it up. I would sketch it out, right? Try to figure it out. Try to figure out what this has to do with parallelograms. Maybe you get some triangles in there, who knows? And see if you can figure this one out on your own. Because I'd rather you figure this one out on your own rather than me tell you the proof. And just say the proof because you're going to remember better if you figure it out on your own. So without further ado, ready, set, and go. 2 minutes on the clock. See if you can figure it out. And then we'll come back together and we'll do the proof after you've had a chance to think about it for a little bit. So take it away. 2 minutes. down the conjecture yet? Have you done the diagram? See if you can just kind of reason through it, come up with the rationale. And then you can check your answer when we go over it on the next slide in about 50 seconds. We'll do that. 50 seconds. See if you can think about it a little bit. Figure it out by now? Because you got about 20 seconds and then I'm restarting this lesson and we'll go over it together. 7 seconds. 4, 3, 2, and 1. That's right. That's right. All right, so maybe you figured it out, maybe you didn't. I just decided to prove it myself and draw this diagram as well, just because, hey, maybe you're just like got stumped. You're like, Mr. Ford, I'm stumped. Take me through it. Make sure I understand why, when we have 3 parallel lines right here, and they're cutting a transversal right here, and they happened to, right, this is just given to us. This is the premise of the situation here. We have 3 parallel lines, and between 2 of those parallel lines and the other 2 parallel lines, if we ran a single transversal through, we would have congruent segments. We're going to make the conclusion, right? We're going to prove here that the other segments, right, of any other transversal they have here have to be congruent to one another. So I'll take you through that. Again, first step is our givens. For this one here, I'm just listing out the parallel lines. We'll get to segment AB congruent to segment BC a little bit later. But I'm saying those 3 things down right now because that's the thing that I'm going to care about a little bit first when I establish something in step 3 for a second. Because remember, I said that this theorem here is kind of a corollary of parallelograms, right? We can use what we know about parallelograms to help us with this. So if you didn't figure out the whole idea about the parallelograms there, the idea is that you needed to add parallelograms to this diagram. So you already have parallel lines here. You have parallel lines here. So question, how can we create some parallelograms within the interior of this here? Well, what we'd have to do is introduce an auxiliary set. Yes, that's right, 2 auxiliary sets here. So through X and Y, draw lines parallel to AC. So if I draw a line parallel to AC right here, or AB if you want to call it, through X, and through Y, I draw another line that's parallel to AC, or to BC if we consider that there, right? Line parallel. I would have a what? What are these going to look like? Here, let's draw it in there. Let's draw it in down below as well. Okay, I'm introducing auxiliary sets through a point outside of a line. I can draw exactly one line parallel to a given line, right? Parallel to a given line. So through point X, there's exactly one line I can draw parallel to AC. Through point Y, there's exactly one line I can draw parallel to AC, and I've introduced those parallel lines there. So getting to this up, this is a big wind up right here. Don't forget, right, over here, right, on this side, we also have parallel lines right here. So look, we have parallel lines here, parallel lines right here, and then this is parallel to that, this is parallel to that. They're not marked like that. So you know what? Quadrilateral ABRX, quadrilateral BCSY, what are those things? They are parallelograms. And that's by definition of parallelogram. The opposite sides here are parallel. Opposite sides of that quadrilateral parallel, opposite sides of that quadrilateral parallel as well. And this is hard to see in the diagrams here, so that's why I'm pointing it out to you. So you have this here, right? This is like looking in detail. You notice it, right? Parallelogram. Parallelogram, and we know because those opposite sides, both pairs of opposite sides of those quadrilaterals are parallel to each other. So we got a parallelogram. There's lots of stuff we know just about parallel lines in general. There's stuff we know about parallelograms. So I'm saying this, and the reason why I saved AB is congruent to BC right now is because what's some things we can say? Well, first of all, these are parallelograms right now. My goal, right, don't forget about the goal if you're working backward. Your goal working backward is that you're trying to get XY congruent to YZ. So actually getting XY congruent to YZ, what do we notice here once we introduce these parallelograms? What are these over here? Ooh, there are triangles that are sort of bounded by XY and YZ and the parallelogram, right? There's this, so a trapezoid, right? A trapezoid, if we changed it, if we drew in a perpendicular, not a perpendicular, a parallel to one of the sides of a trapezoid, it's going to create a triangle over here in a parallelogram, right? A trapezoid is just a parallel. It's not the definition of trapezoid, but a trapezoid would come out if you had a parallelogram, you tack a little triangle to it. So it looks like maybe we can get, our goal here, remember, is to get XY congruent to YZ. These could be some later. We can get CPCTC if we happen to be able to prove this triangle congruent to that triangle, And I might be getting a little bit ahead of myself here, but looks like we got some numbered angles here that we're going to maybe say that are congruent to one another at some point. And in fact, actually, let's not get too over ahead of ourselves right now. What's one thing that we can say is congruent to itself, like pretty much right now? What do we think here? Well, we just said that the in step 3 that the two quadrilaterals are parallelograms, and in step 4, I'm going to actually use that given because again I'm leading you back to the given here. AB is congruent to BC. So sticking with side lengths being the same length, how would I know, for instance, that XR is congruent to YS? Why would I know that? Because I know they're boom boom. Those would actually be congruent sides. Well, AB is congruent to XR. Why is AB congruent to XR? Well, those are what sides of a parallelogram? They're opposite sides of a parallelogram, and opposite sides of a parallelogram are congruent to each other. We can use the same reason for BC being congruent to YS. Opposite sides of a parallelogram are congruent to one another. And here I'm lumping together steps. So notice here I wrote down exactly what I just said about the two pairs of sides of the two parallelograms here. But then I'm making a statement here that XR, boom, has to equal YS, right? Has to equal YS. Well, a couple things going on here. That's opposite sides of a parallelogram are congruent. So yes, the opposite sides of a parallelogram are congruent. Opposite sides of a parallelogram are congruent. We know that AB equals BC, and AB equals this, and BC also equals that. So we're using the transitive property on top of this to make our ultimate conclusion here, because the goal, right, our sort of mini goal, lots of goals in this proof, right? There's lots going on, lots to experience here in this proof. So, but like one of our goals is to show that this triangle is congruent to that triangle. So ultimately, we do want to say XR is congruent to YS, and we're allowed to do that through transitivity. In fact, and I didn't write this down, this is the transitive property applied twice. Yes, because XR is congruent to AB, or at the distant length XR equals length AB. And AB, what does AB connect to? Oh, AB connects to BC. So XR connects to AB, connects to BC, right? But BC connects to YS. So notice here, right, we have to go through 1 to 2 to 3, right, via 2, right? So we can say BC is congruent to XR by transitivity, but then, right, BC is also equal to YS, so because XR equals BC through transitivity earlier, through transitivity again, right, XR would equal YS because they both equal BC. So here I wrote just transitive property, but we probably should have written transitive property applied twice. Okay, anyways, I got a little carried away with that one. So ultimate goal here, get XY congruent to YZ. That'll be through CPCVC. So now I got a side of these two triangles. That's very nice here. How can I get these triangles congruent? How can I get them congruent to one another? Let's look at this here. What do we notice here? Let's start with maybe one of these angles here. So we get one of these angles here congruent to one another pretty easily. Yeah, we can get, how about angle 5 and angle 6? What do you notice about those? Well, remember, I circled it over here. These two lines are parallel to one another, and you know what? XZ serves it as a transversal, right? Again, our whole goal is to get that the two segments that are cut by the parallel lines of the transversal are congruent to one another. So, in fact, we know that these two angles are going to be congruent because these are what types of angles? Corresponding angles. And when we have two parallel lines cut by a transversal, we can make the conclusion that that corresponding angles are congruent, and that is by that postulate that we had in chapter 2. Okay, so angle 5 is certainly congruent to angle 6. How about angle 1 and angle 2? The book's kind of leading us that direction to be able to prove that angle 1 is congruent to angle 2. What's going to make it that we can say angle 1 is congruent to angle 2? Because notice here, these are not corresponding angles. Look at this here. So there are two parallel lines, but not a single transversal cuts these two corresponding angles right here. We have a transversal here and the second transversal over here. So these are not corresponding angles here. So question, how might I justify that angle 1 is congruent to angle 2? Oh, wait, we haven't talked about angle 3 and angle 4. The book wrote that down, that this is angle 3 and angle 4 for a reason. So somebody make a case. Somebody justify for me. Who sees it? Who's going to be able to justify this one? Angle 1 congruent to angle 2. Why? Maybe talking about angle 3 and angle 4. Ooh, I just hit my button by mistake. Yeah, here I got it. Again, this is going to be transitivity applied twice here. So angle 5 congruent to angle 6, that's the easy one. These are just corresponding angles because we have parallel lines cut by a single transversal right here forms angle 5, angle 6. So we know those are congruent. Angle 1 is congruent to angle 2, but we have to do some steps in between. Angle 1 is congruent to angle 3. Actually, yeah, why is angle 1 congruent to angle 3? Well, here we introduced a line parallel to AC. A line parallel to that is XR, right? Is definitely XR right here. So this would fit the definition of corresponding angles. Notice here, what's the transversal of that? That's this middle line. This middle line here is the transversal from these two parallel lines. So even though this line here is parallel to these two, it's technically the transversal of these two other parallel lines right here. Same deal with this bottom line right here. It's a transversal for angles 2 and angles 4, which are cut from these two parallel lines, right? These two parallel lines, the one that we introduced, and then AC, and then AC. So we know angle 1 is congruent to angle 3, corresponding angles. Angle 2 is congruent to angle 4, corresponding angles. And then wait a second, how are we going to link those two together? Well, angle 3 is congruent to angle 4 because you know what? Those are also corresponding angles, right? Line AC now is the transversal. So really kind of messy. Hopefully you look at it, hopefully you spend some time on it and kind of get it, but we're using transitivity again this year. We're using a whole bunch of transitivity on that one. But the whole idea is that we're going to know that angle 1 is congruent to angle 2 because they are, for mainly transitivity, but the idea of getting angle 1 congruent to angle 3, that parallel lines cut by transversal, corresponding angles are congruent. 3 to 4, same exact reason, 3 to 4, and then 4 to 2, same exact reason. So we're kind of using transitivity like 3 times right there. It's kind of messy, certainly messy, but you can get there if you try, if you put it there. Okay. So what you probably noticed about the diagrams, I just sort of wrote up what step 7 was a second ago. But if we notice about the diagrams here, getting those two angles pretty darn important, right? We got those two angles right here, and then we got this side, right? Very nice. So we remember from chapter 3, right? Because we're all rock stars here at this geometry stuff. That when you have two pairs of angles in one triangle congruent to two pairs of angles in another triangle, and you have a side congruent to a side in the other triangle or corresponding side in the other triangle, then the two triangles are here to prove that they're congruent. Okay, but then you got to ask yourself, is this side, is it included or not, right? Is this going to be ASA or is it going to be AAS? What is it? Is it included or not included? It's not included. So this is going to be AAS. Yes, AAS. So the side is kind of off to the side here, not related to that angle at all. So this is the AAS theorem, right? Theorem here. We got those two triangles congruent to one another. And finally, are you awake? Guys, it's been going on a while, right? If I do this in class, I'm all animated. I'm all jumping around. People in the hallways are like, Mr. Fortin, you're going nuts on this proof. But I hope you're awake. I try to keep you awake because I got to explain this stuff. Man, it's my job. It's my job. So you might be put to sleep by now. But hey, you're awake now. You're staying awake because, my friends, what's the last step of the proof? Yeah, buddy. XY is congruent to YZ. Y. CPC, TC. All dramatic, right? The dropping of the question marks. We know this is true, and then boom, stay awake. CPCTC, we are good to go. Okay, so we got this crazy old theorem. Man, that's a lot of work to get to a theorem that doesn't come up a ton, but we'll practice some problems with that a little bit later in class. Yes, my friends. If 3 parallel lines cut off 2 congruent segments on one transversal, then they're going to cut off 2 congruent segments on any transversal that crosses those 3 lines. And just in case I didn't beat that one to death enough here, I want to point out another thing. So obviously, when you're given diagrams in class, you might be like, okay, cool, like, this segments given to us is congruent to that segment, and then that line that was like kind of drawn in already, yeah, man, those 2 segments were congruent to one another. So cool, yes, that's definitely true, but I want to make sure you're interpreting this theorem as broadly, right? As broadly as it can be interpreted. Because here, I got it written out, so make sure you've put this in your notes. If you haven't put it in yet, make sure it goes in your notes. But if three parallel lines cut off congruent segments on one transversal, then they cut off congruent segments on every transversal. So it's not just that transversal that was drawn like right here in the last document. What was it? XYZ? Was that what it was? XYZ? These three parallel lines, because, right, they know our if is fulfilled here of the theorem. If they cut off congruent segments on one transversal than any other transversal. So let's go ahead and draw one that looks kind of different here. I'm going to draw like a little bit more perpendicular, but not quite, maybe like an 89-degree angle, 88-degree angle. I'm going to draw another line. I'm going to do LM, line LM, and might as well make this one N. So I got line LMN here, okay? This is a different line, right? The other one was like more like this. This one's a little more like this, but right, with this transversal, it's still going to be true, right? It's still going to be true. And I'll put a question mark up here, and let's just like go through that last proof kind of again, and I'll prove to you, right, that these actually are, right, going to be congruent to one another. So think about it. If this is a different transversal right now, your steps to actually proving this are the same exact thing as you did before. First step, right, you had to introduce that parallel, right? We introduced this thing parallel to AC. And we introduce through point M another line that is parallel to AC. And I'm going to put the tick mark down there just so you see right there, okay? What all of a sudden we have? Well, these are parallel, right? There's a little parallel somewhere here. These really should have 2 tick marks because the 1 tick mark's already taken here. All right, put 2 tick marks in there. And maybe we'll put the 1 back over here, right? Now we see it a little more clearly, okay? If you didn't see it when I was going over that last proof, look at this. Boom! That is a parallelogram, friends. This is a parallelogram as well, right? Parallelogram as well. So what we know here is that with a parallelogram, what do you know about opposite sides? Opposite sides are congruent, so I'm going to mark that up. Yes, because this is the same as that, and this is the same as that, and this is the same as that. These are congruent to one another, right? These are congruent to another right here, okay? Boom, what do we have? Parallel line there, transversal, right? Transversal. So remember, I just put the triangle in, but remember, this is just transversal before. So what I really could have done a little more clearly was mark this up right away. Corresponding angles are congruent, right? Corresponding angles are congruent, okay? And then a little more slowly, you might have had trouble like really realizing why that angle was congruent to that angle. So I'll do it a little more slowly right here. Well, check it out. This here, because this and this are supplementary, right? And then this is supplementary to that, right? Another way you can justify that these guys have to be congruent to each other, okay? But also, right, more simply, corresponding angles, right? Corresponding angles, like those are definitely congruent to one another, okay? And look at this here, right? This angle here, it's not just a corresponding angle with this angle right here. This angle corresponds to that angle too, because we got AC as the transversal right here. Okay, you follow me? Angle, the same, and this is the same. And by the same logic here, boom, this line parallel to that line, and then this bottom line, a transversal, congruent. And we have 4 congruent angles. The thing we really care about is this one being congruent to that one. And finally, we have that these 2 triangles, triangle LXM and triangle MWN, are congruent to each other by AAS. But that wasn't my goal, right? That wasn't my goal, was to get 2 triangles congruent. My goal was this, to get LM congruent to MN. And remember, I just drew this transversal in randomly, and we're going to get out by LM by CPCTC. We know that those 2 segments are congruent to one another. And hey, getting this fact established was key to getting that every transversal, right? Every transversal, this is going to be the case because that happened on one transversal, and transversal congruent segments formed. So boom, we got it with a different transversal. I showed you that they're the same logic. It's going to happen each and every time. Okie dokie. So I said we had 2 theorems today. That was the big one. The second one's kind of big. Yeah, it's not nearly as big as that last one, but it's related to that last one. Okay, so that's kind of cool. So here, I haven't updated the language for this theorem yet because this theorem, my friends, is related to our next theorem. In fact, this is actually called its corollary, right? This will lead somewhere. So we're going to have to get 3 parallel lines, it sounds like. All right, so as suggested by the diagram on the left, this guy's going to have a corollary. So we're looking at this here, and one thing that I noticed right away is like, wait a second, why is this a corollary that I have in front of us? Because I don't see 3 parallel lines, right? I don't see 3 parallel lines right here. Well, first of all, actually, what is this? What is this? Let's try to see if we can surmise what this diagram is being shown to us here. Okay, so it looks like this is a little bit more specific than this theorem that we have up here. It looks like we're given a triangle, okay, a triangle, and we have a line, okay? We have a line that goes through this M here must be the midpoint of AB. So if a line goes through the midpoint of the side of a triangle, it sounds like, and what else? Oh, it's parallel to the side it doesn't intersect, or to the third side, right? So if it goes through a midpoint of the side of a triangle, and it's parallel to one of the other sides, then it's going to do what to the final side, the one we haven't talked about it yet. It looks like it's also, right, if this is true, if we can prove this, it looks like it's also going to bisect the other side, right, the other side here. Okay, so that's kind of wordy too, and you might be thinking, how are you going to prove this? Well, it's a pretty easy way to prove it. I'm going to go ahead and show it to you right now. Boom, booyah. Hey, look at that. Look at that. How about that? This is going to be proven. We just need to figure out what the wording of this theorem is here. Because, boom, what did I just draw in? That's right, friends. I drew an auxiliary set, an auxiliary line. So through a point outside of a line here, or a point outside of this line here, there's exactly 1 parallel that you can draw to that line, or to that line, because these are both parallel to one another. That a line parallel to that guy also be parallel to that guy. Anywho, that's the diagram we're going to use for this. Let's see if we can get the wording of this one now. So if let's hear, if a line that contains a midpoint of one side of a triangle and is parallel to the other side of the triangle, then it will bisect the third side. Okay, so we're calling this, okay, we're calling this, I guess, kind of like side 1. Side 2. So if it goes to the midpoint of the first side of a triangle, and it's parallel to a second side of a triangle, then it's going to bisect the third side of the triangle. So it'll go through the midpoint of the third side of the triangle here. So that's kind of interesting. Just the fact that it's parallel to the side it doesn't touch and goes to the midpoint of one, it's going to have to go to the midpoint of the other. And this sort of gets us to the idea again about parallel lines being preserving space, right? Preserving distance, okay? Distance is usually measured as a perpendicular distance here, but if we slant it, right, if we slanted and kept it consistent in terms of its slant here, that this would match that, because distance is preserved. It looks like these are all equidistant from one another. This distance, the same as that distance. So, anyways, if you didn't see kind of what I did here too, this theorem. You don't have to worry about the name of this theorem, but what I call it is the midline theorem. I think it's maybe in the other textbook, the one that Mr. Sin students last year used. It's called the midline theorem. That's right, the midline theorem. Okay, so this we'll call a midline because it goes through the midpoint of one segment. It's parallel to one of the other sides. It's also going to go through the midpoint of the third segment, the third side there. And right, this is kind of like a midline of a triangle. That doesn't really come up again the rest of the book, so don't really worry about it here. Okie dokie. So what we need to do is we need to talk about our givens. And we talk about our proven. So here, this one isn't written out as an if-then statement, so it's a little bit harder to figure out what your given is and what you're trying to prove. But here, we got a line that contains the midpoint of one side of a triangle, and it's parallel to the third side. It bisects the third side. Okay, so the then statement is basically then it bisects the third side. So we'll get to that later. We should think about what we're given here. So if I guess a line contains the midpoint. So if line MN, if line MN is parallel to BC and M is the midpoint of AB, that's kind of what I would say. Let's see what they say. So they say the midpoint thing first. So M is the midpoint of AB, and then MN, so therefore M is the midpoint. So it goes through the midpoint, and it's parallel to the third side. Yeah. So N, right? N we can maybe call the midpoint of AC. If we can prove that MN is the midpoint of AC, then through definition of midpoint, we'll know that MN bisects AC. Okay, so think about it for another second or two. I'm going to just keep going with. I'm going to move on to the theorem right now because hey, let's just jump into it and see what we got. Why didn't it fly? It should have flown. Fly, darn you! No, it's not flying. Let's just go on to the theorem right now, see if we can prove this guy and get on with our merry day. So here we go. Let's do it. Statements, reasons. Step one, who's got me, who's got me? That's right, a given. Putting down the midpoint thing, putting down that MN is parallel to BC. So again, we're trying to prove just this is congruent to that. So we can't really do that because we're not really going to have like congruent triangles right here. That's not going to happen. So remember, this is a corollary of what? Ooh, we need to talk about here in our given premise, we're only talking about two parallel lines. How many parallel lines do we need to be talking about? That's right, three, right? Three from the last theorem, which is a corollary of the theorem. Three parallel lines cut a transversal and two congruent segments are formed, then two congruent segments are formed on the another transversal. So without further ado, we need to talk about the third line that's parallel to the other two lines. What line is that? Well, it's already written in this diagram. I sort of drew it in the last one. That is line AD. Through a point outside of a line, exactly one line can be drawn parallel to another line. So we'll draw in that line AD a little bit later because I wrote the proof in a different order. But anyways, let's say that AM is congruent to MB. Yes, let's say that. Because we haven't actually said that yet. Look at that. In step one, we didn't say that because we're given that M was the midpoint of segment AB. So what are we using in step two? We're using definition of a midpoint. By definition, that's going to create two congruent segments. And I needed to say that because I needed to fulfill the idea of the theorem that if we had three parallel lines and two segments are congruent, right? You need to say the two segments are congruent, then this would have to be congruent to that. So, all right, so I fulfilled one part of the hypothesis of the theorem that we're using to prove this corollary. So what's the other part of the hypothesis? Okay, we need to talk about the three lines. So I need to draw that line. So it was in the diagram the book gave us, but you know what? Like you need to draw it in because really you're just in this theorem that you're proving, you're just given this triangle really. Okay, so we're going to draw AD in such a way where it's parallel to MN. Okay, through MN. So through point A, we're drawing a parallel to MN. So through a point outside a line, exactly one parallel can be drawn. Okay, so can we use the old theorem? Can we use the theorem that we proved towards the beginning of class, right? Towards 15 minutes into class is how long it took for us to prove it, right? Can we use that theorem, right? If three lines are parallel to each other and they cut off two congruent segments. So we got the two congruent segments part, but guys, have we actually said that the three lines are parallel to one another? No, not exactly. We've said that AD is parallel to MN and MN is parallel to BC. So this is the kind of thing where it looks like kind of like by transitivity, right? If AD is parallel to MN and MN is parallel to BC, kind of through transitivity, we would know that all three lines are what? Parallel to each other. Okay, so there actually is not a transitivity. So reminder, there's not a transitivity postulate or theorem or property, right? Property of parallelity. There isn't a transitivity reason for that. So how am I getting it that AD? Why would I know that AD is parallel to BC, for instance? So notice this here. I just rewrote this with the three things, right? Because remember the theorem that we proved just before this. Let's look at our givens there. We're given just the three lines are all parallel to one another. So we need to say that in order to use that theorem. So really the only new information that I have right here is that I'm just trying to get AD parallel to BC so that I can say this. Because I already know that this is true. I already know that that is true. So if it's not transitivity, what is it? It's that weird one where they kind of word out transitivity. So if two lines, right, AD and BC are both what to MN, are both parallel to another line, then those two lines are also parallel to each other, right? Parallel to each other, or worded kind of like that, right? Worded kind of like I did. It's good to go. Okay, so now I've established we have three lines, and they're parallel to one another. And those three lines, well, they cut off congruent segments on one transversal. Perfect. So you know what? We can get two steps away from proving this because now we can say what? That these three lines will cut off congruent segments of this transversal right here. So we can say AN equals NC. the distance AN equals distance NC, or length AN equals NC, and because of the theorem that we're using to build this corollary upon. Okay, so just a property of triangles, right? We run something parallel to one of the sides, and we run it through the midpoint. It's gonna hit the midpoint of the other triangle. So this is definitely important for designing triangles and understanding how triangles work. It's also gonna help us with stuff in chapter 5 as we get a little bit more precise with this and have more applications to this, where kind of similarity, right? Because ratios will get preserved, right, between different sides, and that's kind of interesting stuff. So, anyways, we've proven this here because in step 5, obviously, if this segment's congruent to that segment, or this length is the same as that length, that is going to be enough for defining the fact that this gets bisected, because this got bisected, right? These are two equal sections here. So we've done and taken care of this as our proof. We've gotten it done. Hooray, we got that done, and that just leaves one thing for us. That's right. Oral practice, or not really oral practice, because, hey, I figured let's just do some B-level problems with for us right now. No reason to mess around with those A problems, right? Those A problems, hey, you're fine. You can do those by yourself. You can do those with your group. You're gonna be A-okay. So how about some B problems? Some B-level problems. Good old Mr. Fortin. Let's do it. Let's boogie. Let's get down with it, okay? Let's just do number 11 together first. Then I'll give you a minute or two to number 12. You can check your answer, and we'll get on with our merry way. Get on with our days. Get the heck on out of here. So let's just kind of do this one together. All right, let me mark it up here, okay? So in this one here, I don't just have 3. I have 4 parallel lines. Cool. All good, right? All good in the hood here. We got AB is 15 lengths, and BC is 2x minus y, and CD equals x plus y. Then x equals what, and y equals what? Let's see. I think I'm missing kind of something here to this problem. What am I missing here? I'm going to go to the actual textbook, because I think what they must have given to us here in this problem was that AB equals BC equals CD. So let me just double check in the textbook, because this happens sometimes where, there we go. Yep, they're giving us this. Okay, they had another given to us here in the textbook here, and that's we have these parallel lines. Cool, we see it. They're telling us again up here, but hey, they're also telling us that EF equals FG equals GH, so we can make the conclusion that AB has got to equal BC, right? Because it's going to cut congruent segments on any transversal. And BC is also got to be congruent to CD. So we can make any of these, we can use any of these as statements of equality. We can set up basically an equation here. Let's do the first one. We can do AB equals BC. So AB equals BC, which means that 15 equals 2x minus y. Okay, that's one equation. Oh, interesting here. I see what they're doing here. I see what they're doing to us. And then we can set up another equation, another relationship here, that BC equals CD, and BC is 2x minus y. In fact, you know what? I got an easier way. I got an easier way for you. I do. Check this out. We can do, because BC equals CD, and you know, these are all equal to each other. These are all equal, these are all equal. So I got an easier one for you. Check this out. Okay, I'll do this in a different color so that you can see this a little bit more clearly. I can say that CD and AB are equal to one another. And check it out here, because we're talking about AB here. AB is 15. So AB equals CD. I also know that 15, in the first problem, I knew that 15 had to equal 2x minus y. In this problem, AB equals CD, I know that 15's got to equal x plus y. So what does this look familiar to, you ask? Does this remind you about Algebra 1 and all, right? Algebra 1 and all? Okay, 2x minus y, it equals 15. X plus y also equals 15. So these, 2x plus y, and x plus y, they equal the same thing. They equal the same thing. So this, by using the transitive property or equal values method, as they call this in Algebra 1, we're going to be able to solve this problem. Do you remember this is called when we have more than one equation, right? More than one equation that shares the same variables, and we're going to have to use those more than one equations to figure out what those variables equal. This is called a system of equations, and we can use transitivity here, or the equal values method, to figure out what x and y must equal. So what I can do is I can set this 2x minus y equal to each other, x plus y. Okay? Next step is I can subtract x from both sides and add y to both sides just to combine like terms. And let's see what I get. I get 2x minus x. That's just going to equal x. Negative y plus y is 0. And y plus y is 2y. Okay, so I get x equals 2y. Is that really solving our problems here? Well, x equals 2y and y equals, I guess, half x, or does that make sense? No, they actually want numerical answers right here. Okay, so this is actually more, there might have been actually a better way of doing this, but what can I do actually to solve this right here? Well, if I know x equals 2y, can I actually use either of these equations to figure out what my answer is here? What about this up here? Okay, if x equals 2y right here, and x plus y equals 15, what can I do with this x to solve this problem here? Can I drop in 2y for x right here? Okay, 4x right here? Sure I can. 2y equals x, as I proved earlier, using that transitive property and simplifying. So I can get that down here. So 15 equals, instead of writing x, I'm going to write 2y, and then I'm going to add y to it. And I get 15 equaling 3y. So divide both sides by 3. I'm going to know that y has got to equal 5. Okay, there's my one answer. So y equals 5. What is x going to have to equal? Well, x plus y equals 15, so that means x is going to have to equal 10. X is going to have to equal 10. Man, that was kind of a messy problem. A bit messy right here, right? A bit messy, okay? So what I was going to do with problem 12, right? Problem 12 was have you do it yourself. But, hey, I think that was kind of harder because it's maybe been a bit since Algebra 1. You might not have known how to do that. You still might not know what the heck I was talking about. So if you struggled with that one or you're having trouble following my reasoning right here, please, please, please pay attention because I'm going to do number 12 with you too. And we'll just end class with me doing a couple problems with you guys here. Okay, so this one's written a little bit differently here. Here we have AB and BC. Those are congruent to one another. But, we have BD. Okay, we have BD is 8x here. So interesting here in part 12. Part 12, we have this distance represents by 8x. Okay, 8x. And then the smaller half of that distance can be represented by 2x plus 3y. Okay, so now you're going to use that. Can I actually come up with an equation here? 2x plus 3y is this little guy here. Twice that is going to represent 8x. So yes, I actually can come up with an equation here. What I can do is if I multiplied this segment by 2, I would get 8x, right? So I can multiply 2 times by 2x plus 3y, and that would have to be equal to 8 or equivalent to 8x. Okay, so that might be one equation that I have that I can use in a system, right, for a system to solve this problem, this one here. Okay, I also know that AB, right, AB is 12. This distance here is 12. And what do I know that 12 relates to 8x, for instance? Well, if this is 12, 2x plus 3y, that also equals 12. And this would also have to equal 12 here. So 8x actually has to equal 12 times 2, right, which is 24. Okay, so another way we can think about 8x is that it's going to be twice as long as that 12-unit one that we had earlier. So 2 times by 12 equals 8x. And in fact, this is a lot easier to solve here, right? This one here, we can actually solve for x right now. 24 equals 8x. And divide both sides by 8, we get 3 for x, and we get our answer very quickly. 4x is 3. So So yeah, this was definitely an easier problem actually than 11 because you only had one variable here. And then you had a constant here you could relate to. So you can just solve for that one variable very quickly. All right, so now we got to get y, right? Now we got to get y. I think instead of dealing with this equation right here, I'm just going to cross this out because we can actually set up another equation here that's going to help us get y because we know that 2x plus 3y, instead of twice it equals 8x, that's doing too much work. We also know that 2x plus 3y equals what? Well, I wrote it over here. Equals 12, right? Equals 12. What else do we know about this? How are we going to get y out of this? Well, we know from earlier that x equals 3, right? X equals 3. So we can replace x here with 3, right? With 3 to get our answer. So instead of 2x, I can write 2 times by x, and x is 3, so I'm doing 2 times 3. And we're adding 3y to that, and that equals 12. And I'm going to be able to solve for y fairly easily here. 2 times 3 is 6, plus 3y equals to 12. And now we just need to isolate y. Subtract 6 from both sides, so I get 3y equaling to 6, right? My 6 goes away because I subtracted 6 from that side also. 3y equals 6, and then y equals 2. Very obviously equals 2 there, but you can also do the division property of equality, divide both sides by 3, you get y equaling 2, and we have our answer there. So this problem is a little more tricky, actually, so I'm glad I did it with you guys here, especially because it's been a bit of time since we've solved systems, and we may need to review that. We'll check back and see how we feel when we review homework together. Okie dokie, folks. Man, remember those 2 theorems we just did? Whew, really put them on out there, and then it's on you guys to hopefully figure out the homework, and I'll support you guys along the way. But important thing was that I introduce these theorems to you guys and realize it comes from a place, and then maybe take a look at some systems problems here. And this is super messy. We can go over this again a bit later if you would like to. Okie dokie, that's it. This is what I'm thinking of as homework, something like this, right? Oh, we have 11 and 12.